Okay, so we'll just go in, I guess it's the alphabetical order of the first names of the various presenters. I kind of calculated, I think we can afford like 7 minutes per talk. Some of you interpreted 4 slides to be 11 or 13 slides, so I'm sure you will run into trouble. So 7 minutes, hard stop. Whatever slides are left over, they are left over. So Eden and Matt.
All right, let me know when I can go.
Yeah, you can start.
All right, so my partner Aiden and I are doing real-time activity classification using wearables. So our overall goals, we want to use wearables to classify and detect similar activities in real time. Specifically, we're using the eSense wearable and the MotionSense HRV wristband. The activities that we selected were chosen specifically because they are historically difficult to classify using a single sensor, and so we're hoping that using multiple sensors and different types of data, we can get a better classification accuracy. In the end, our deliverables will be an analysis of the classification accuracy with and without certain sensors. So we want to compare the use of both sensors and all of the data to maybe just using a wristband or just using the earables. And the activities being eating, drinking, smoking, they're all very similar. Using one hand, you couldn't really tell the difference, but we're hoping that using both, we can differentiate between them. So for our technical approach, the eSense wearables, they're different between the left and the right. The left one has a 6-axis IMU. The right one gives microphone data, and the MotionSense has a 6-axis IMU. We take this data and pre-process it. We separate it into sliding windows. Right now we're using 1-second sliding windows with a stride of a quarter of a second. That might change depending on our model parameters. For the audio, the MFCC is basically transferring it into the frequency domain where we calculate a number of features on that. We extract features from the time domain signals as well. After that, I'll talk later about why we chose to do feature extraction instead of just putting the raw input into the CNN. But we take that, put it into our CNN. This outputs a classification for every activity window, and then we smooth that output and get our final activity classification. So for our experimental setup, we basically had to connect every device, even the earables, the left and the right, to a different device. So the left earable was the IMU data, and it was collected through an eSense tester app run on an Android phone. The right one was connected to a computer, which collected the microphone data. And the wristband was collected on another Pixel through an M-Cerebrum app, which is the company that developed the wristband we were using. And to get our truth value, the M-Cerebrum app has an option that lets you basically say where an activity starts and stops. So we would say, we would hit the start button, our subject would take a drink of water. When he finished, we would click stop. So we know when the different activities started and stopped for training in our model. Because we were hooked up to 3 different devices, after listening to the timing lecture, we realized that our data was going to be not synchronized. And so we implemented a script recently to synchronize the time. What we ended up doing is taking the earable that has the IMU, putting it in our hand that had the wristband on it, and doing a punch, which corresponded to an impulse on the accelerometers for each, and the sound you could hear on the microphone. So we could find what time that was at and sync it. We ended up syncing it to the wristband's time, because that's what gave us our truth value for the activities as well. So pre-processing for our network, a CNN can usually take raw input. So basically we could have fed the accelerometer straight into the CNN. But the problem was in our hardware, the sampling rate was a bit all over the place. It wasn't giving us a uniform sampling rate. And so for a CNN, you need the same amount of inputs for every window. And so instead, we decided to calculate features for each of the windows. And for the time domain, we use stuff like mean, standard deviation, range, correlation, and a few more, as well as some frequency features. And this is what the layering of our CNN looks like right now. So our current status, basically, we have about 4,500 instances in our data set. Given this data, we can synchronize the time, separate it into windows, perform the feature extraction, and then format the data and save it. And then given data, we can separate into training, validation, and test set. And we do have a compiled model with some preliminary results. Going forwards, we want to collect some more data. We want to continue to tune the model parameters to improve our performance. We want to compare that performance when we take out certain sensors. And then we want to hopefully be able to develop an Android application that can interface with all of the devices at once and port our model into that application using TensorFlow Lite for real-time classification.
Okay, great. Let's see, how are we doing on time? 2 minutes, so I can ask some questions. So why did you have to connect the two ear sense to one to laptop, one to Android? You can't.
Yeah, so we wanted just to be able to train our model very quickly to start, and there wasn't really any software where we could connect to all of them at once. We actually used an app from Brian in your lab who could get it for the eSense, and then the only way we could quickly get the data for the HRV was to use the M-Cerebrum app, so we had to use a different phone for that. And the app that you guys had didn't do microphone and IMU at the same time, so then we connected to a third device to get the IMU.
Okay, and the sample rate being all over the map, is that
Yeah.
Was that present in all the 3 cases?
Yes.
Okay.
Yeah.
So it's not
We looked at the
something you
data
can
for
provide.
the wristband. We looked at the data for the IMU, and they just didn't have a uniform sampling rate. And so it was, if it was within a margin of error, we were thinking about, okay, we could still do raw input by just taking, instead of saying the window is exactly half a second, we could say it's 50 samples or something like that. But the sampling rate was variable enough that we just felt like, okay, we should take a time window and then just calculate features on it.
Okay.
We spoke to another team that was using the eSense as well, and I think they had a similar issue with them.
Yeah.
Okay.
Sorry.
Yeah.
So,
Sampling rate is all over the place.
Yeah.
okay, we have 45 seconds. Any audience question? No one? Okay. Thanks.
Thank you.
Can you move to the next slide?
Yeah.
Okay. Go for it.
Good. Okay, cool. Hey everyone, so I'm Gabriel Byron, and our group is doing locating and visualizing wireless signals. So introduction. So I'm going to run through a bit of how this is going to work, I guess. So I guess the main point of the project is to be able to locate a wireless signal, at least the source of it. So there's been a lot of research done to this field, and a lot of people use antenna arrays, which generally consist of about 8 arrays arranged in an L shape or a circle. The problem with this is that it's kind of difficult for consumer devices to have maybe like 8 arrays. Just takes up a lot of space. It's kind of hard to manage. But we found a paper that suggests that you might be able to estimate the location using just 2 antennas. And this depends on the fact on this equation. So we find that these left 3 variables we actually know. So the phase difference is kind of the difference in timing when the 2 signals arrive to the 2 antennas. The distance between the antennas is fixed, and the wavelength is known for a lot of things like 802.11 Wi-Fi. So the things that we really need to know in order to actually locate the signal are the azimuth angle and the elevation. So let's suppose the maybe like a Wi-Fi router is directly ahead of me. In this case, the azimuth angle of that is pi over 2. If it's a little bit to the right of me, the azimuth is somewhere between 0 and pi over 2. And if it's directly to the right, this azimuth angle is 0. But what this means is if we keep the distance between the antennas fixed, the wavelength the same, and we don't change the elevation, the only thing that really changes is the azimuth. So if we know that the Wi-Fi signal is directly ahead of me, that means that the cosine of that is 0, which means that the phase difference becomes 0. Also, if it's directly to the right of me, cosine equals 1, so we end up with the phase difference being maximized. So based on this fact, we can estimate the azimuth angle, and we can do something similar to estimate the elevation. And given these 2 angles, we can actually, if we were pointing the camera in the direction of this wireless signal source, we can use these 2 angles to kind of translate that to a location in an image. So the overall goal is to develop sort of an AR application, which, given this the location of the signal, we can kind of draw a rectangle around it and kind of like follow it around the room. And we can also kind of capture some information, like maybe packets from a Wi-Fi signal, and display that to the user. So our technical approach is to, we're going to use two USRP devices as our two antennas. And we're using a GNU radio to, I guess, find the phase difference. And then we're going to develop an AR application running on a Surface Pro. We use OpenCV to draw the rectangle and also do some basic image tracking. And we also use the accelerometers and the gyroscope to also track the user's position. So currently, a lot of work has been put into setting up the new radio modules, which turns out the documentation isn't as good as we thought it was. So it's kind of more difficult to find the phase shift than we imagined. So right now, we're able to capture a Wi-Fi signal on our two antennas, and we can capture packets. So we're using that right now. We're trying to figure out how to get the phase difference. We also got OpenCV and the Windows sensors working. So we've set up kind of some demo applications. So basically, once we get the phase difference from the two USRP devices, we can connect it to the, I guess, the Windows demo we have working, and this should all come together. So that's all we have.
Great.
Yeah.
So what's the issue with the phase difference? I mean,
Yeah, there's not very good examples online. We found a good example to at least get the two antennas receiving data, but calculating the phase difference is a little more complicated.
okay, and since you're receiving the two signals on two separate devices, so how are you going to calculate the phase difference given that they are not time synchronized?
Yeah, let me pass it on to my other group member.
We're going to connect this to USRP device together.
So you can synchronize the two together.
Yeah, in order to receive the phase.
Okay.
Yeah.
Okay. And I didn't quite understand. So what's the connection with the camera out here? I mean, in the sense.
Oh yeah.
Is this purely visualization?
It's visualization. So basically, once we get the location of the object, if we point a camera at it, we can like draw a circle around it.
Okay.
Yeah.
Okay. Anyone else with questions? No. Okay. Great.
Cool.
Thanks.
Thank you. Okay.
Okay.
All right, hello everyone. My name is Kian. The project that I'm working on is a REM sleep tracker. One of the things that I noticed is that I sleep a lot and I don't know if the sleep I'm getting is any good. So I decided I would want to kind of investigate that and put my hours in bed to good use. So yeah, the overall project, sleep studies are expensive and impractical. If you actually want to go in, you have to schedule an appointment, you have to have a prescription, or not a prescription, a doctor's note, and it looks something like this. That doesn't look very comfortable. And obviously you're not going to have that set up at home. And also they have the Fitbit trackers or any other kind of watch or motion tracker. And that's not actually a good indicator of REM sleep. It does detect motion, but REM sleep has to actually do with the actual rapid eye movement, which is not going to be able to be tracked by a watch or other wearable. There are currently a couple of headband solutions that are able to track the actual raw EEG brainwaves. There's two companies, one called Dream and one called Muse. And that data is accessible and useful for tracking sleep. However, it's very expensive. It runs anywhere from $200 to $700. So my solution aims to be cheaper and also more comfortable because it's difficult to fall asleep with a big headband on. So the approach that I took is to basically have two sensors. One of them is going to be a 9-axis IMU that's basically mounted onto a sleep mask, so it'll sit directly on your eyelid and detect those rapid eye movements. In addition, there's a pulse sensor that'll just be attached to your finger. So there have been studies that show when you enter REM sleep, your brain becomes more active, you're kind of dreaming. Even though your body is immobile, your heart rate does increase, so that's another data point that we have there. And then, of course, Professor brought up a good point. Well, you can track the eye movement and you can track your pulse, but how are you going to know whether it's actually REM sleep or not? And so in order to do that, he was nice enough to buy one of those expensive headbands, and I've been testing this on myself and wearing the headband while wearing these sensors and trying to get this EEG data. So this Muse headband here, it has 5 different electrodes and it can sense all the different types of waves, and we're looking for alpha, delta, and then theta waves, and then that will lead to a state of REM sleep, which happens around every 90 minutes. So there are these sawtooth waves that come into effect at that point. So the current status, all the hardware is fully assembled. I've been testing this on myself, and it hasn't been that fun, but been doing that for about a couple weeks now. So the actual headband has a built-in gyroscope and accelerometer, so that's been useful for time synchronization. I'll just do like a very specific head pattern movement to indicate that this is what I'm going to be starting at. I'm taking samples every 1 second, and I was able to write Python scripts to basically automate a lot of the starting of the heart rate sensor and the other IMU. So far I've seen these measurements correlate with EEG data. As you can see here, there's a decrease in the delta, increase in the theta, which indicates the start of a REM sleep cycle, and that correlated with some spikes in the heart rate sensor and also with movement from the IMU sensor. So I'm working right now to set up the convolutional LSTM that will actually be able to classify the REM sleep, getting a little bit more training data, which has been difficult to measure at times just because I move around in my sleep a bit and the headband comes off. So other than that, I'm striving for an accuracy of 90%, and labeling the data, I want to get within a window of about 2 to 3 minutes to detect a REM cycle, and those happen around every 90 minutes, as I said before. And yeah, that's it.
Great, thanks. So, anyone with questions?
Mm-hmm.
Could you explain that graph right there? I see the delta and the theta, but what are the other?
Yeah, sorry, I cut out. There's more, but they're the other types of brainwaves. There's beta, alpha. So alpha waves are going to be happening when you're wide awake. Beta is when you're in like a calm state. Delta is when you're entering deep sleep. Theta is in the deepest sleep, and after that, it's REM sleep. So as you can see here, there's a decrease in delta and a spike in theta right around the 2:20 a.m. area, and that's when I'm classifying it as REM sleep.
So REM is classified as what precisely?
It's the end of the theta cycle. So once the theta increases at the end, after you've seen alpha, then delta, then theta, then you enter REM sleep, and it takes typically around 10 minutes.
And I guess intuitively your goal is to just detect the eye movement via
The IMU and the pulse sensor, that's correct, yes. And those sensors are about $30 total, so a lot cheaper than 200
so
or
is there prior
something.
work which has attempted to do that, and how well?
Well, the prior work has all been in a lab, like in a sleep lab, and then they have I forget what they're called, but they sense the electrical impulses of the eye, and that's how they detect eye movement. So it's a little bit more complicated than just an IMU.
Okay, great. Can you, anyone else questions?
You said using IMU for tracking eye movements.
Mm-hmm.
How do you exactly do that?
So it's the IMU, I basically embedded it into a sleep mask.
Uh-huh.
So the sleep mask is sitting directly on my eyelids, and when my eyes move around, then the IMU will pick that up.
Okay.
And another thing that I've been doing is, because the headband itself has an IMU in it as well, I will like cross-reference the data and make sure that it's not just my head moving around, it's actually just the eyelids that are moving.
Oh, okay. Yeah, because I was like, for just to win that false positive.
Yeah, so I basically take them and subtract them off to make sure I'm not just picking up me moving around in my sleep. It's actually just the eyelids.
People use like those like rotary encoder, like you can actually like count the number of times that actually like your eyes is moving. Like they use it on for more like robots, or if you want to like kind of like control different motors and you just use those encoders. I thought like it might be interesting to look into, but if you cut it like it's perfect. Yeah, that was interesting actually.
All right.
Thanks. Can you move on to the next slide?
Yeah.
Okay, so my project's pretty simple. Basically I'm designing a software application to control a smart home, more or less. It's just an application that takes in data about human behavior residents in the smart home and learns temporal patterns about what the human's doing. And then once it learns that, it becomes intelligent in the sense that it'll start to preempt when the humans or the residents in the smart home actually do those things, like turn on lights or change the temperature, open, close doors, windows, etc. So, like I said, project objectives is just to develop this software platform that learns from human-computer interactions, and then it will start to predict and preempt these utilizations of smart features in the smart home. And then ideally, I say ideally, I'll explain later, but the machine learning backend is going to be implemented on the cloud. So I didn't put enough pictures in my slides, so I'm going to use the board. Essentially, the pipeline is pretty simple. It's just, if this is the smart home. There's a controller that's residing into the smart home that's doing all the data processing and control. And then finally, that's wirelessly communicating. The controller is wirelessly communicating with the cloud, which is running the machine learning algorithm. So the machine learning is usually trained on like a better computer with more resources, more memory resources. And that way I don't have to put it inside the control loop and limit the frequency or the control rate of the controller that's playing with the smart home. So yeah. And then the second idea I had, which I won't have time to implement this quarter, but it's good to think about. I also, after gathering a lot of data on the machine learning side, I would also use unsupervised learning to basically just look at the a metric that between functions, for example, like time series trajectories of human behavior. I would start to cluster all these trajectories by a functional metric. And then once I've clustered them, then you can kind of categorize them, or at least you can't maybe semantically identify them, but at least you can identify them in the sense that, if I just choose like a k-means clustering algorithm, there's like k different, common trajectories. And then the humans can say, hey, we're going to go on vacation and we're not going to do these trajectories usually. So we'll turn them off, take them out of the machine learning algorithm training data set. The machine learning algorithm will retrain on a subset of the data that's only relevant, and then it'll quickly update how the home behaves, predicts things. But that's something extra. I don't have time to do this quarter. And obviously optimize the performance of Party Home, and the trade-off is really just how fast the machine learning algorithm can slowly adapt. So what happens is I pre-trained the machine learning algorithm on let's just assume history. I could just pre-train it to nothing, like just set everything off in the house. But I pre-train it to history, and then as the residents use the house more, it'll just keep warm training or partially training the machine learning model until it slowly converges into what the humans want to do. So it's kind of like adapting to resident behavior over time. Pretty simple. Okay, and the deliverables is just the algorithm, the smart home algorithm that's running on Python. It just basically it takes in observations from all the features in the smart home, sends that to the cloud, or actually I'm running the ML on my PC, so it would be run at the edge in this case. But it would takes the data, sends it to machine learning algorithm, updates the model, uses the model to control the smart home. That would be that part of it. And then also some auxiliary MATLAB code. I actually had to pull a lot of real smart home data from houses in Milan, Italy, and Kyoto, Japan, just spying on people using their homes. And essentially that MATLAB code was just to quickly translate that data into the periodic or sampling frequency of the controller to quickly convert data sets into relevant data to be used on the machine learning algorithm. And then also finally the analysis of the performance of the model after I optimize it for like what I would consider a good enough convergence rate. And by convergence rate, I'll explain in the next slide. Okay, so the design and tech that I'm using, or the concepts at least I'm using. So I'm using imitation learning. Imitation learning is a type of reinforcement learning. The only difference is, while reinforcement learning algorithm learns a reward function, which is essentially given a current state, what reward do you get from an action at that current state? Instead of doing that, I'm just learning the policy directly. So you get more information from the reward, but this is just much more straightforward if you just directly learn the policy. And by policy, I mean it's a map from the current time and the entire state of the home to giving you the prediction or the next state of the. Okay, thank you. The next state of the home. And then, the algorithm overview is simple. It's exactly what I said before. Observe the time state, predict and actuate the following state, receive feedback on human overrides that change what the prediction would have been, and partially train the model on that feedback. And technology I'm using Home.io. It's a fantastic simulation algorithm that I can just control everything in Python without much worries. I guess there's some weird bugs with timing, but I got that all figured out in the code, so that's fine. And I'm using the CASAS data set from Washington State University. The data is pretty crappy. It's literally just a time series sequence of different sensors in the house turning on and off. But then some people have written annotations, which are actually the data that I'm using to construct my data set for the human behavior in the house, and the MATLAB program that was doing that. So completed objectives, I already have the control algorithm. It works really well. I can even fast forward the time to like 4 times, or not 4 times actually. The 4 times time acceleration is actually just running through a whole day of simulation in 17 seconds. So that's really fast. And my controller works with that because of the timing algorithm and control algorithm I wrote. I've done the data collection. I literally just read through multiple days of data. I don't need that many days of data. I'm going to depend on the adaptation part of the learning algorithm to do most of the updating. And I've done the pre-training, which is just essentially initializing the model to a pre-trained data set, or training it to a pre-trained data set. Leftover objectives, I still have to write the adaptation and then optimize it more or less, and analyze the performance of that adaptation part of the training. And extra objectives, like I said, the unsupervised learning, it's really just adding a separate parallel machine learning algorithm that's clustering all the data and then separating the data into pieces, and then I can immediately delete or include that data into the training of the machine learning algorithm and also implement it on the cloud. That's it.
Okay.
Yeah. Any questions? Yeah.
Which kind of accelerator do you use? Using the
Oh no, I'm just using scikit-learn because I realized like TensorFlow is like taking a sledgehammer to this problem. Right now, I'm only learning the behavior of lights and other Boolean features in the home. Even temperature though is just a simple regression problem that I can just use in MLP. But I guess I could. I mean, I can't say that TensorFlow won't work better, but then it's really a sledgehammer for this problem. I don't need it. I'm just using scikit-learn. So like I said, you're learning a policy that just gives you the next state. You don't really need an accelerator for that. Like because the frequency of my controller is about 10 minutes. Like every 10 minutes, the smart home changes all the lights on to the next state and stuff like that. And within 10 minutes, you have quite a lot of time to train. So you don't really need acceleration for just enough for all the variables that describe a smart home.
I'm confused now. So you are predicting the state 10 minutes in advance. Is that correct? Or whatever. Every 10 minutes you are changing the.
You'll have to
setting of
wait
the
till the
home.
next day for the updates too. So like the period of the window, I guess, of training is a whole day. So
Okay.
yeah, like once it learns in one day,
So
you only see
train
the
it one day and then you apply that point. So
Yeah,
so
more or
it's
less.
24 ahead. So what is the logic behind a day? Like I mean, if today is Friday, tomorrow is Saturday.
Yeah, that's
Saturday
the
is going to be very different.
yeah. So that's something that isn't included in my design. But to include in my design, what I was planning before was I would have to have multiple models, or not multiple models. I would have to more like, okay, sorry, this is the fastest way. The dumbest way to do it is just extend the window to a whole week instead of a day. But then that would be a ton of data, and then I probably would need a accelerator and a better machine learning model to do that.
Yeah, but why not simply have different categories of days, like weekdays and weekends? And
Yeah.
then,
I can do that too. I can just add another
and
variable.
what if your prediction is wrong? What will the home do?
Yeah, so
I guess I'm
Human
kind of pushing
override.
the premise in a way out here, right?
human
So it's
human
prediction.
override will always win. So if the machine learning so there's a lot of aspects to talk about. There's safety critical aspects, which is like the machine learning model shouldn't do crazy things. It shouldn't do things that essentially jeopardize or
I think that's the one. Can you move to the next slide?
yeah, sure. Sorry, but that was,
yeah.
is that a satisfying answer?
Well, you should make sure that you address these things in the.
Yeah, I'm only playing with lights so far, so it's really just a power loss, I guess.
Okay.
Hi, I am Glenn Marowitz. I am planning to use embedded sensors to recognize weather patterns that can degrade autonomous vehicle performance. Sadly, I couldn't get a picture of the Cybertruck in the rain.
With the unbreakable glass, right?
The rain would have broken the glass, so that wouldn't be safe for other reasons. So, autonomous vehicles are, so typically they are meant to operate in a limited operational design domain. So that's something that can be based on geography, right? So it could be, hey, we only operate below the 38th parallel. It could be weather, we only operate in the sun, time of day, we only operate between noon and 4 p.m., or kind of any other parameter that defines this domain. And that's because the different operating conditions can greatly impact sensors that you have and algorithms that you have to figure out how are we supposed to drive, right? So embedded sensors that a lot of these AVs use include camera, LiDAR, radar, ultrasonics, kind of you name it, it's probably on there, IMUs, GPS. And each of these will be susceptible to different failure modes depending on weather conditions. And so changing ambient conditions If it's raining, that's going to impact your camera. If it's snowy, that might impact LiDAR in certain ways. Lighting will impact how cameras see things. That should impact how you change how your vehicle drives, right? So you wouldn't want it to be going the same speed on a snowy road as it would on a normal road, just as hopefully you don't as a human. So this is a chart over here from some pre-existing work that shows how humans change their behavior in varying conditions. So you can see, that speed decreases as bad conditions are more prevalent. One thing to note, that identifying specific weather patterns and ambient conditions simply via camera or from any of these sensors is quite difficult to do. So what am I specifically looking to do is actually do just that difficult thing. So try to create a labeled database of images and video showing a range of different ambient conditions that you may experience on the road. Train a neural network to identify and classify these images and conditions, and then deploy that to an NVIDIA Jetson Nano with a Raspberry Pi camera to try to emulate what a car or what an autonomous vehicle would see. And then ideally looking to actually create a little custom environment where I can alter the ambient conditions, quote unquote, to actually verify that the system works as expected, and then ensure that the system properly adjusts some kind of internal finite state machine to say we've gone from good weather to rain or to fog or to snow, and thus we should alter our driving conditions appropriately. So I am looking to use VGG16, and so that's just a large algorithm that's used, this one, for training neural networks, pre-trained with ImageNet, so that's just like a classification set of 10, 15 million images, something like that. And then I'm going to be training it on Keras, that's on top of TensorFlow. I currently have a data set of about 1,300 training images that I'm using a variety of road conditions, and just training that on my laptop, just with this size, takes a fair bit of a weekend to do. And then use the NVIDIA Jetson Nano, that little thing over there, to deploy it for actual inference testing. Here are some pictures kind of what my data set looks like. So right now I have, for instance, rain images, snow images, dust images, and night images. All of them are different road conditions on how these impact the roads. So where am I right now? I've trained a neural network on the initial data set, and we have about 80% accuracy, which is what we have here. And then I'm looking to improve the accuracy to try to get to, I'm targeting around 90% or better. And I'm going to have to, fine tune the data sets that I have. I just downloaded a huge number of images from Google, and improve the accuracy that way, and then deploy to the embedded system. Large number of references, and are there any questions or comments on any of that?
So, do you know if, like on cars like Tesla, are they using only the image, or like rain also has sound, for example, and also are they using other modalities? And also, I guess there is the motion aspect, namely image versus video, right? So what goes on in the current system?
That is a good question, and I think the answer depends a lot on the specific company that you're talking about. So Tesla is actually one of the companies that's been a little bit more open with what they're doing. And so Andrew Karpathy, who is the Stanford computer vision expert who is now at Tesla, he's given a few talks which are really good and kind of detailed into their techniques, specifically about vision. I don't know if they have what other sensors, I guess, go into that, but he mentions how they have some very extensive framework to support detecting certain classifications of objects at all times.
So what sensors? Are they using video or images?
I have no idea.
Okay.
I do not know the answer to that. I do not know if that's public information. Yeah.
But
Yes.
you are only looking at images.
I'm only training it on images, and then I'm going to be deploying it to video. Yeah.
Okay. Another question.
Yeah, so what will happen like if there is like a combination of these conditions? Like suppose it's night and it's raining.
For right now, obviously the network would pick one and you'd classify it at one. I don't have dual classification. That is something to work on in the future. Yeah. Yeah.
Are you training with the Pi camera, or these are just like images taken?
Sadly, I cannot collect my own data because we don't see too many different different weather patterns in Southern California. So the data set that I have now is from Google Images. Yeah. Anyone else? Okay.
Okay, great. Can you flip to the next one?
So, that's team one. Our topic is the pedestrian alert system using wearables. And the main goal of our project is using the audio information to recognize the approaching cars in their direction, and then use the RMU information to determine the position of the user's head, and then develop a mechanism to alert the user if the user is not aware of approaching cars. And the most challenging part is the first one. So this presentation is going to mainly focus on the first goal of our project. And so the first part of our project is the hardware setup. So we totally have three phases of it. And at the beginning, what we want to use is the Nokia eSense wearables. And then you can collect your audio information with the microphone instead of the two wearable, and then analyze the signal, then calculate the time difference between the two microphone, and then find out the direction of the cars. And the problem with that is the first one. So even though they have a microphone in both unit, but only one can activate it while connecting to your mobile phone, and you cannot connect two different pairs of eSense earbuds to the same phone because of the Bluetooth protocol. And then that's why we moved to the second phase. And the second phase, we try to use wired microphone to collect the audio information and somehow split it into two channels. And there are two wire connectors we're using in our project, but both of them doesn't work because of after I collect the sample from these wire cables and run it on the MATLAB, we found out the signal in left channel and right channel just totally same. There's no difference. So what we think of it is somehow input the signal of each microphone and then add them together, then average the signal into each channel, so that there's no signal difference in each channel. And also, we realized that the single mobile phone doesn't have ability to split the input into two channels. So that's why we moved to the third phase. And the third phase is we use two different phones to collect the audio signal. And the most challenging part of this part, and we analyze the sample we collect offline. And the challenging part of this approach is that we have to synchronize our two-channel signal like perfectly, because the time delay of the two microphones could be just 3 milliseconds. So your synchronization have to be really perfect to detect the small time difference of two microphones. So that's our overall hardware setup. And so next part is the signal processing part. We basically cut our audio signal into different frames. The frame size we choose for this project is 100 milliseconds, and then we move and we slide 2 milliseconds every time we choose a new frame, and to detect the time difference. And the feature we're using in this project is called non-uniform binned integral parallelogram. And what it does is basically it transfers the signal of the single frame from time domain to frequency domain, and it set a frequency threshold somewhere, and it cut the whole frame into different bins. So in this example, there are 5 bins, and the signal we care the most is the signal that's at the lower frequency, because the car noise frequency is basically around 200 hertz. So that's why we mainly care about the signal at the left part of the threshold, and we basically integrate the information signal of different bins, and we perform some machine learning model to grab feature of different bins, then train the whole data. And there are 2 machine learning models we are using for this project. One is called one class SVM, and another is called isolation first. After comparing these 2 different machine learning models, we found out the isolation first works better, because as you can see in the left part, once it detects the signal, detects the car noise, it somehow goes up and down, so which is not good in our project. So, and on the isolation first part, once it detects the car noise, it remains at the detected status, and that's what we want in our project. and we choose the isolation first module to train our signal samples. And for the synchronization part, what we do is basically, so when we collect the audio signal, we use a tone generator to generate a 1 kilohertz tone while we collecting the audio signals. And when we calculate the time difference between the two channels, we also do a FFT of our signal in the single frame, and we are looking at the signal at 1 kilohertz. If the energy is above a certain threshold, in our case, we set it to 10, and then we consider that frame as the first frame of that channel sample. And that's how we do the synchronization. And in this case, the difference between the delay between two channels is about like 0.5 seconds, which is reasonable. And after performing everything, the result we got for the very first sample we are testing is we correctly detect the direction of the sample, and the time difference we find out is about 0.018 seconds, which is about like 18 milliseconds, which is much larger than we thought, and that's something we should work on in the future. The difference by the ideal difference should be around 3 milliseconds. So this could be because of the two phones different, and it could be the model training part, and that's something we should figure out in the future. So basically, our current status is we already finished the hardware setup, and then we already finished the noise detection, and like very early phase of the direct detection. And the next step gonna be focusing on the IMU information extraction, and then change some parameter of our signal processing part, like let's say shrink the window size, and modify the window overlap percentage to optimize the direction detection. And that's our project.
So, what did you mean by from left to right? Like right now, you're saying you're only able to say is the car on the left or the right, or is it? Okay.
Yeah, because we only have two microphones. We set the microphone position to be like at the pocket position. So with the two microphones, you can only tell the car is from the left part or the right part. You cannot tell the car is from front and
you're
back.
different to that. Okay. Front versus back, you can't, right? Okay.
Yeah.
But you are still aiming to get the angles, right?
Angle part we haven't done.
We haven't done
that yet, but maybe something we can focus on in the later time. Yeah.
Okay. Question? Anyone else? Great. Thanks. Can you move to the next slide?
Sure.
Hi everyone, my name is Amir, and that's Julian and Ria, my teammates. Our project involves indoor navigation system for visually impaired people. Excuse me. So we try to like come up with a voice command app that like users can use in order to navigate through the room. So it'd be like just like giving the blind people commands on how to reach like different places inside the room. And then for the localizations, we're using ultra wideband communication, and then I'll talk about how it works later on. And then once we get the data and then like everything's localized through the server, then we just like calculate the shortest path, and then just like let the user know how they can like approach the things that they're looking for. So this is like the diagram of how our system works. So basically for the UWB, you have the tag and the anchors that like we placed in the room, and then like the position of them actually hard coded to the server. So we know like where the tags, where the anchors are, and then for the tag, the way it works is basically calculate the time that it takes to arrive from the anchor to the tag, and then based on that it calculate and then now that we know the position of the tag and the anchors, or the anchors, and you can basically calculate the position of the tag. And then the protocol we're using for that to communicate with the server is MQTT, that basically give you these ability to kind of like subscribe or publish different messages, and then you can read it from the other clients in the same network. Along with the UWB, we're using another sensor that actually gives you the pose. So for example, if the blind person is walking this way or is actually like, this like 90-degree angle and all. So it has a IMU, it has an accelerometer, gyroscope, and magnetometer, and then like we just like getting the position and the pose based off that. And then on the other side of the server, and then we have the app that it actually like talk with the server, and then like user can like this is the user interface, so like they can ask where they want to go, and then it would like kind of like go through this whole loop. But then the problem with UWB is that it has like 20 centimeter inaccuracy, and that wasn't like very good for our case because like it's like too much when we want to like approach like different appliances, let's say. And then we're using Bluetooth beacon. So the idea is like you have to like place each of these beacons on top of like each appliances, and then like once you're pretty close to that, it actually goes based on the signal strength. So like when you very close, it starts like vibrating, and then like that way like maybe we can like kind of like address that inaccuracy rate for the UWB. And then this is like the this is our room that we're testing it, and then this stars are the anchors that we placed. We started with the 4, now we have 8. Not that it really helped with increasing the accuracy, but it's slightly better. And then these are the like microwave, fridge, and coffee maker. We actually like hard code their positions, and then like user can ask to approach them or actually like get a path to them. And then these like the big obstacles, we also have to like put them inside the server, so like we know like how to avoid them, and we try to like give them like a path. And current stat is that like we have the communication all set up. So on one side we have the app, and the other side is, like I said, the UWB, and is working. And then we have a short demo that I can like go over. And then the other thing is like that we have to add, like we have some problem with the pose. And then the other thing is we have to add the pose, because right now we're using like 2 different microcontrollers, one for the pose sensor and the other one is for the tag. We have to like integrate it together and then make a variable out of it. And the app, I think we still have to like kind of, there's just like some bugs with text to speech and the other part of it that we receiving the data. And then we were thinking of like actually adding the eSense at the end, so like then the user the earballs with them, like then the user don't need to like hold the phone or move around. So we also like thinking of like implementing that at the last step if we get the time. So this is like very quick demo, if I can play it here.
Recording.
Please specify a destination.
I want to go to the microwave.
Walk for 3.5 meters. Walk for 3.3 meters. Walk for 2.6 meters. Walk for 1.9 meters. Walk for 1.0 meters. You already arrived at your destination.
So like one thing to mention, this 3D map that you see there, we have some contribution to that, but this is not our own software. We did not like did it from scratch. This is just like from another project that I think HCI group used, and then like we building upon that, adding more sensors, and we actually using that for debugging our system most likely. And then the other thing is like in this demo, as you can see, the pose was not working, so I had to like, after we figured out the problem with the pose sensor, where did it go? Oh yeah. So like this is like another very quick one after we fixing the pose estimation, so just to show you it's working. And these are just the UWB anchors that we placed at different levels in the room. And yeah, over there.
So one quick question. You are referring to Bluetooth, but normally Bluetooth has much worse accuracy than
Sorry, I don't know what
autoplay and you yeah.
Well,
But normally, I mean, Bluetooth accuracy is a lot worse. So why do you think that will help you?
So it's actually a threshold. So like after you get like pretty close to the appliance, I mean you're here, but then let's say like that 20 centimeter. I mean we haven't really tested with blind people. I don't know like if it's the case. But you're saying like if that 20 centimeter matters, like let's say you have multiple objects here, and then at that close up proximity, then you can just like use the signal strength from the Bluetooth just to make it vibrate a little bit, and then as soon as like you're grabbing it, you can deactivate it.
Okay, anyone with question? Let's move on. Next one.
Right. So, hi everyone. My name is Dan, and my group is tackling audio and video synchronization. So, our overall project goal is to first detect the offset between audio and video streams because they can get out of sync during transmission, and then create a system that extracts the audio and video, synchronizes it, and then and synchronize it in one go. We're trying to reduce the lag to 45 seconds for audio leading the video because that's more detectable. So, and for deliverables, I'll describe what we will deliver here. So we will use ShareX to capture the computer screen. So for now, we're just gonna try to capture desynchronization on a computer, and then in the future we're going to try to transfer this onto mobile devices. And then so after we capture the audio and video, we're going to use FFmpeg to separate the audio and video, then run the audio and video through our neural network to obtain the offset, and then finally inject the offset into the VLC media player. So we've tried 3 strategies for obtaining the offset. Strategy 1 consists of just using a straight CNN from the audio and the video frames and audio spectrogram, just use straight CNNs and output the offset. But that didn't work because the offset was random and our model ended up overfitting a lot. Strategy 2 avoids neural networks altogether, and instead of using video frames and spectrograms, we're going to try to detect the mouth, and instead of like continuous values, we use 0 for closed and 1 for open. And then for the voice branch, we use something called voice activity, where 0 means not talking and 1 means talking. So once we have both binary streams, we correlate them to find the offset. So that's our way to do it without neural networks. If we get that one working, then we could like speed up computation and also make embedded implementation more feasible. And then the third strategy is essentially inspired by a paper called SyncNet. And what SyncNet does is takes sliding windows of 5 frames each, and also MFCC audio voice features, and puts them through similar networks. And then on the outputs, we have 2 vectors. So the goal of this network is to identify false and genuine pairs. And what false genuine pairs means is genuine means the 2 inputs correspond to like the same time frame, so they're aligned, and the negative pair means the audio and video streams are misaligned. So we're trying to train this network to recognize genuine and false pairs. And then the way to get the offset is to manually slide the audio back and forth to find the minimum L2 distance between these 2 vectors. So basically maximizing the number of true pairs. And yeah, so we've been trying many different video features, including like grayscale face the entire frame itself, which actually is a bad idea because the face has a lot of extraneous features, while speech only involves the mouth. So that's why we decided to try mouth aspect ratio using DLib. And what DLib does is identify points on the face, and we use the lip points to say whether the mouth is open or not. And then the voice activity I've already explained. So for the current status, we've successfully gathered some videos from the internet of a single person frontal pose because that's the simplest scenario. We also generated sets of aligned and misaligned segments of those videos. And we also implemented the 3 strategies on Google Colab. And finally, we have our screen capture and time injection components. So for screen capture, we're using ShareX, and in time injection, we use VLC on the command line. And for our next steps, since we're dealing with a lot of overfitting, we have to obtain more data. We should record our own videos, search for more videos on the internet of single-person frontal speakers, experiment with additional video and audio features, and also implement data augmentation, which involves like shifting the video a little bit, flipping the video to artificially increase our training data. And then once our overfitting is resolved, then we optimize the hyperparameters, and then finally we build the system together. And that's it.
Questions, anyone? So I didn't quite understand the logic of why you are doing this one way, like you said, audio leading the video and the other way. Why is that? Why is that? Is it easier or?
I guess it's easier to just deal with one case first. Okay. Yeah, and we decided to go with audio leading because from personal experience, like when we're watching Twitch or YouTube, the audio stream usually arrives first while the video lags.
Okay, great. Thanks.
Alright, hi guys. So my name is Nicholas, and me and my partner Eugene has been working on the project Distributed Digital IoT Assistant. So the overall goal for this project is that we try to design a system that can understand what people take in as a command and make the system can understand and map it to multiple devices, including the sensors and actuators. And the whole project can be broken into 3 parts: the baseline, in which we know exactly what we're trying to interact with, but we are trying to just identify what we're trying to interact with. And second is that we don't know anything, and the system will be able to understand the actions, the appliance or the system that we're trying to interact with, and the last is the parameters. And the last one is the stretch goal, which is that people don't have to say exactly what they're trying to do, but the system will be able to interpret based on the simple sentence the people input. Oh, and so the whole system is based on the audio input, and the output will be like a multiple command line in the form of tuples. So as I mentioned, the first phase is just we try to identify the actions without the parameters, and the second is that we try to identify the action, appliance, and parameters, and the last one is the variable parameters which over a dynamically device set. Yeah. So here is the flowchart of our system. After the speech is converted into the text, then it is processed by the BERT, which is a state-of-the-art Google-invented NLP model. And then the sentence will be extracted as the parameter-related content and the task-related content. After processing by the neural network, it will be broken into the tuples used to trigger and input parameters for DDFlow, which is another student following Professor's project. Yeah. So here are the few libraries and models we used. The first one is the BERT, which is the basic for everything. The flare is the one we use to handle the conditional statement, such as if somebody do something, then do something. And the Spacey is a Python-based model in which allows us to analyze the structure of the sentence and then organize out the comments. And the last one is the speech recognition, which, as I already mentioned, the whole system based on the input as a voice. So technical details. Spacey is one of the bases of our system. This one allows us to output the form of command as the command, appliance, program, and parameters. So after the sentence has been processed by the BERT, the Spacey will first analyze the structures of the sentence by analyzing each word. For example, here we have a sentence, turn on the light, TV, and the radio. It will first tell us that whether this word is a verb, a position, noun, or just a conjunction. But it would also provide us with the relationship between different words in this sentence. And then we attempted to write a extra layer that would output this kind of tree map into the command tuples like this. And in order to do this, there are a few small tricks we need to apply. First is the sentence streaming, in which we first find the stop words and some useless punctuations, such as the and and in this sentence, because they're not going to be helpful for the Spacey to understand. And second is the position switching position, because there's a limitation for the model we're using, as when we put the position word in different places in a sentence, this Python model would interpret it differently. So we try to organize the sentence in a way that the system can understand overall. And next is the keyword replacement. This is a self-designed file that we just find whatever the verb or the noun to specific appliance. For example, we have the change the temperature to 75 degrees. Then we can see that the change is available is closest to the command set in our predefined command set, and the temperature is closest to the appliance air conditioner. Then we just map the input sentence to the output sentence without changing any structures, so the system can handle some synonyms and acronyms and can avoid some command confusion that could work across different appliances. And the last one is the command branching, which, as I already mentioned, so it turns like one single sentence into different output commands tuples. Right, so right now we're basically done with the first two phases. First is, again, the simple Spacey-based algorithm that only tries to determine the command. And second is after handling many minor confusions, they can determine the action, appliance, and the parameters. And what we're trying to do here for this week, we will try to wrap off the part for synonym and acronyms, because there are we're trying to dig through deeper for different commands for each appliance. And then we will make the recognition model more robust, because right now our current model still cannot handle some complex sentence structures that people may have a low possibility of saying. And then for the last week, we were trying to handle the conditional statement and make the keyword mapping more comprehensive. And then for the stretch goal, we'll maybe have a head start on how to just speak the general stuffs and map it out to specifics. All right. Any questions?
Questions? So what kind of complicated structures you think you might be able to? So if then is one, but then there is also like a sequencing, like turn the light on, then open the window or something like that.
Yeah. So the if statement is we're not actually considering it as a complicated sentence structure, because we tend to use a different approach to solve this. So one of the complicated sentence structure is that people would make multiple commands in one sentence. For example, they may include multiple verbs, but they would change the position word in different positions of the sentence. So that one we tried to like input a like 20 something word sentence into the into our system, and it was only able to like distinguish the like partially. So, and we need to figure out a way for it to go from top to bottom. And
Also, just to make sure, so you start with spoken thing or written?
Spoken.
Spoken.
Yeah.
So how well is that working, the Python speech?
Yeah, it was working pretty well. One thing is that the spoken thing does not output a sentence with punctuations, so we may have to figure out a way to add those like or divide the sentences or add those like commas in the right places for the sentence.
Great. Then move on to the next slide.
Okay.
Thanks.
Okay, hello everyone. So the title of our project is wearable. So MRE stands for Mixed Reality Wearable, and the title of the project is Integrating Spatial Audio in the Mixed Reality Environment through Wearable Sensor Modalities. So this figure basically shows what we're trying to do. So we have a user in the mixed reality environment, and the user is wearing the Essence wearable sensor, which happens to have a IMU. So the IMU is going to transmit the acceleration and the gyroscope data to a machine learning model that's going to estimate your head pose. And the outputs of this machine learning model is the azimuth angle and the elevation angle. And this is going to be fed into something known as the head related transfer function. So what is the HRTF? So basically HRTF takes the azimuth and elevation angle of the head poses input, and given a sound file, it can transform a monaural sound file into something known as a binaural or spatial audio. So basically binaural or spatial audio means how we basically hear sound. So what are the deliverables? So by the midterm, we promised to use the trained head pose estimator to generate spatial audio from a stationary sound source in real time. So we have partially been able to do it, and we're currently trying to improve the performance of it. And finally, what we're going to show is we'll integrate our head pose regressor and the HRTF kernel with a VR platform, any cause VR platform such as Unity. And in turn, we're going to complete a persistent processing feedback loop. So basically, the VR platform is going to like generate spatial audio, and as you move your head, then you're gonna hear binaural sound. So the technical approach, so basically the wearable is a relatively new thing, so there was not enough head pose data, so we decided to create our own data set. So basically here's the setup. So here's the user, she's wearing a Essence wearable sensor, and the blue ones, these are several targets that we set up in the cell. So there are two types of head pose that we considered. First is origin, target, origin. So basically this is the origin, you move to a target and then you come back to the origin. Then the second type of head pose is origin, target 1, target 2, then back to origin. So in total, in the 3D space, we had 27 targets and in total of 34 distinct head poses. Apart from this, we also decided to do some human action recognition as well, and we also collected some activities data that might be important in future in VR context. And here you can see some of the parameters of the wearable sensor that we set up. And for ground truth, we used the OptiTrack system that was already in place at Nestle. Apart from that, we used one of the wearables connected to the laptop for audio inputs. And we also used a video camera for ground truthing the activity recognition. And in order to characterize all of these targets in 3D space, we used the Leica distro laser rangefinder. So the sample data looks something like this. So before we told the user to move his or head to a particular target, we told him to like nod in a particular pattern. And this is quite clear. This is, by the way, a plot of gyroscope's amplitude versus time. So this is the calibration node. And as you can see for origin, target origin, you can clearly see like there are two opposite peaks. So basically these peaks correspond to the head movements. So in total, after cleaning and processing and slicing the dataset, we had 1,266 inertial frames. Out of this 1,266 inertial frames, we took 734 frames and we decided to group them into bins of 20 degrees for two reasons. Firstly, the data was very noisy, and as my peers mentioned, the sampling rate varies very widely. And anyway, humans cannot really distinguish the location of the sound source that are like placed very close, placed closer, less than 20 degrees. So basically, we essentially transformed the regression problem into a classification problem. So basically, the elevation had 16 classes and the azimuth had 14 classes. And for every machine learning that we trained, we ensured that our model doesn't overfit. So basically, we had 3-4 cross validation in place, and we also had hold rate ratio of 90 to 10. So due to the variable sampling rate, neural networks perform really poorly on the dataset. However, after like fiddling around a bit, we found out that XGBoost performed quite well, reaching a classification accuracy of 75, almost 75% after we did a grid search hyperparameter optimization. Apart from that, my peers have also developed this environment in Unity. So here basically you can simulate head pose by pressing several arrow keys on the keyboard. So as you press the arrow keys, the character in this game moves around. And if you are wearing the headphones, then you can actually get a feel of how spatial audio looks like. So basically, in summary, our current status is basically like we have done everything, but all of the stuff is like fragmented. Like we have like trained the classifier on the elevation data, and we have developed several different pieces of software. Like as I showed that my peer have developed a simulation environment in Unity, and we have also developed software to mine instance data into the computer. And apart from that, I also like try to find out how Kalman filters would perform, however they don't perform that well. So what are the next steps? So in summary, the next step is to integrate all of this stuff like the head pose regression model, the HRTF kernel, and the 3D sound testing platform that I just showed. We want to integrate all of this into one. And we'd also like to improve the classification performance of our head pose classifier as well. And apart from that, we also need to like complete the training on the Azimuth classifier since we only like did the elevation training. Okay, thank you. Questions?
Questions? Anyone? So just to understand the high level thing, so
Okay.
the idea would be that you are projecting artificial sound in this VR space, and I'm not quite sure what once you're complete, what would it feel like to a user?
Okay, so basically you are in this virtual world, and basically the wearable sensor is tracking your head pose. And suppose there is a static sound source, for example, there.
In the virtual world?
Yeah.
Okay.
And suppose you move your head like this, then the head-related transfer function will be able to detect your azimuth and elevation, and it will in turn give you the binaural spatial audio.
Okay. So you are creating synthetic audio sources within Unity then?
Yep, that's right.
Okay. Okay, great. And so right. So you haven't you don't yet have any results on how well the head pose estimation is working, right?
Oh, yeah, we do have. You can see the classification.
Oh, okay.
We do have that. But we need to improve this a little more.
And that is only for
No,
the
but
elevation.
since you have converted the regression problem to a classification problem, so you have lost the notion of distance. So right, so is it like if I misclassify to a neighboring class, in a regression sense, it's okay, right? I mean, instead of here, I just decide here. But in your case, if instead of here, I do it here or I do it here, they're both the same, right?
Not actually. Like if you do it like here and then you are doing it like in that direction, the results will be different.
But in your classification accuracy, they would be the same because of the, so you have lost the sense of distance between the classes.
When we observe the confusion matrix for the classifier, we assume most of the errors were within 1 or 2 class range. And our classifier right now is also dominated by certain classes because of lack of.
I guess what I'm trying to suggest is the following: while you may have treated it as a classification problem, the appropriate error metric is not class error. The appropriate error metric is still L2 norm or something like that, right? Because there is, like you said, I mean, if I'm misclassifying totally in the opposite direction, that's much more wrong than if it was a neighboring class.
Yeah, that's right.
Okay, so you might want to kind of use the right metric for it.
Yeah.
Okay, great. Thanks. You're doing it?
Alright, so our project is EMG-based control and expression for personal devices. Our overall project goal is to be able to use a gesture recognition algorithm and use that for you to interface with your personal device, like your computer or your phone. So specific aims of our project is to first create a set of gestures that we can use to implement and for specific tasks and stuff. Second is to develop a feature extraction algorithm and implement that into our neural network. And finally, we want to be able to translate that gesture recognition algorithm into an Android application just to show how we can interface with your personal device. So first of all, just a real quick overview. Depolarization and repolarization of your skeletal muscle cells are what we get from an EMG. And we're going to be using the Mile armband right here in order to gather that data, and we're going to be connecting it via Bluetooth to our Android devices. So the set of gestures we have grouped up already is the whole hand movement, where we would be moving like so with the whole hand. And then we have single tap movements where your finger would just move up a little bit, and that would vary depending on your finger, right? So how we're going to approach our EMG data analysis is going to be through a sliding window approach, and that's just to capture the time domain, and we're going to be separating that into it's going to be separated into segments, and segments make up a window, and that's just going to slide across our data set. And we have 8 different channels, and the 6 parameters are MAV, which is mean average value, root mean square, slope sign change, waveform length, and AHP and MHP are the JORT parameters. So the way we're going to set up our data is first we're going to reduce the noise that we get, and then we're going to classify that, and then we're going to extract our features. So in total, we have 20,000 samples per whole hand gesture, and we have 3,000 samples per single finger gestures. And our neural network architecture is just an input layer with 48 nodes, which is the 6 parameters via the 8 channels. And our hidden layer is just going to be sigma 1 activation with 24 nodes. And our output layer just depends on the number of classes we are going to finalize on. We're using Python and TensorFlow, and we're going to be implementing, showing that demonstration via Android Studios. And this is just kind of the pipeline of how we're going to classify our data. So first, it's the noise reduction, and then it's the classification, and then it's going to be that feature extraction. So just to clarify right now, we have about like a little over 80% accuracy with each finger tap. And how that's going to correspond to within our device interface is if you go up, if you move your index finger up a little bit, then it will correspond to like the letter R on your keyboard. And we're trying to implement that with each finger. So we're trying to show functionality within as much keys as possible with just one hand, because we only have one Mile armband. And we're just going to input into the keyboard on our Android device that way. And essentially, the whole hand movement is going to correspond to a cursor that we're going to place on the screen, and you'll essentially move that with those 4 directions of your whole hand movement. So currently, we have the Android application, and it's coupled with our EMG data. We just need to create some kind of activity where you can actually demonstrate how we're going to type and show the movement of the cursor. We do have our defined gesture set, so we have settled on using the left hand and then a single tap movements for your index, middle, ring, and pinky finger. And our core data set is complete, so we have, like I said, a little over 80% accuracy in determining what gesture you're actually using. So upcoming tasks we still need to do is we just need to finalize our data sets, finalize our neural network, and just merge that TensorFlow code into our Android application. And then we just have to finish all the technical details with reports and websites and such. And that's it. Any questions?
Yeah, so I thought you guys were not using the Mile band and you were preparing the whole hardware.
Yeah,
What
yeah,
happened?
we
The
were
project is very different than what you.
Yeah, originally we were doing the PCBs, but then we ran into a little issues with the filter system, so we just decided to save time. We'll just
So
use the
since
Mile
there is a
armband.
lot of work and papers on using gesture recognition using Mile band, so
Mhm.
one of the things I would like to know is that what is different between the
Yeah.
prior work and what's the prior work
Yeah.
and what is the increment that you guys are bringing, because Mile band probably like a few dozen papers. around
Yeah,
that, right?
well, all the Mile band papers that we've read only do whole hand finger recognition, so they haven't classified a single tap yet, which is what we're going to implement that into directly, like you're essentially tapping onto your keyboard.
Okay.
So yeah, everything else is just like rolling or whole hand movements essentially, because that's a lot more easy to classify than single tap movements.
Being more exactly, there are papers on recognition even of one paper movement, but nobody have done a tapping to the best of our knowledge.
Okay. Okay. Make sure to bring those things out, because I mean,
Yeah.
now that you have not doing the hardware component, okay, so so you are sort of in a bit of a crowded space, so you need to make sure that you highlight what has gone on.
Mhm.
And So there are two types of prior work you need to highlight, right? One is with MyoBand, what have people done? And the other thing is specifically for these single finger taps and all, without MyoBand, what all people have done, right? I mean, because, like, for example, I know people have done smart gloves kind of things and all where they put sensors, right?
Yeah, but that's all across like your fingers and stuff. But
Right,
this
right,
is just
right.
a MyoBand connection.
Yeah. So I think, but they're all related work.
Okay.
So the thing is, you do need to kind of make sure that you highlight and bring out what the differences are and just acknowledge what currently exists.
Okay.
And how does your performance compare with them, right? I mean, it could be that, yeah, they have done it, but their accuracy is not better, for example, or maybe capabilities in some regard. Okay. So make sure to do that. Great. Anyone with questions? Well, are silent. Okay. Great.
All right, so my name is Iru, and our topic is WebAssembly exposure to IoT device. So first of all, what is WebAssembly? WebAssembly basically is a very novel language, just appeared in 2017, March 2017, and it's mainly for web design to replace JavaScript, and it is only used in web browser by that time. However, right now people are thinking of using WebAssembly out of a browser because it is such low profile and it is faster and it's more secure than normally C and C++. Well, the overall goal of the project is to test recent WebAssembly runtime to different devices and check the possibility of implementing those into existing, implementing the existing function on the runtime. So we are doing the several testing on various of WebAssembly runtimes on streaming platforms, Ubuntu, Mac OS, and Windows. We use there's two versions of data test that right now is one is cosay.wasm, the other one the masm.edge is just a reference for any function inside the mass.edge, and we can convert that into WASM and go running on WASM runtimes. And there's a different compilers. We can use CLAN and the SDK, the mscripting SDK was provided by WASM actually. And mainly right now there's three language supporting, right? The Rust, C, and Go. So we test, those are the main runtimes we tested right now. And this is basically the average runtime you can find in GitHub. So the most successful I would say right now is the Wasmer. It is, you can see everything is filled up. It used Rust, C++, and excellent compiler, and got it even got the package manager by itself called WebPM. I would say WAPM. So we tested all of those runtimes on three platforms. Some were success, some were failed, and I will explain those later. So this is a cosay file. You can see that's the outcome. What you do is just you import a string, for instance, hello world, and you choose the characters, lovely characters, and it will output the character, the scene in the terminal, and this is used for the Wasmer, and you can see there's a new version for the Wasmer, which I just updated my Wasmer last week, and there's a new version already existing. So I will say the Wasmer right now is the most, the best one right now. And we got a lot of issues actually. Since WebAssembly is a very new technology, I would say, every step moving towards our final, the object goal, there's a bug exists, like every single time. And the thing's really tricky is we don't know what caused that, because the runtime itself is not well built. It's not like Windows, like you just click the .ext file and you got your something installed in your computer. It's not like that on the runtime. The runtime itself is not well built. So everything you try, every new things you try on a runtime, there's some magic existing, I would say. So currently we tested the PC reference for like the Mac, also Ubuntu and the Windows. And the Raspberry Pi, we test some function on Raspberry Pi, and there's only a few runtime supported Raspberry Pi right now. So the next step will be we try to, like I said, we try to convert our C code, some basic function in math.h, convert those to the WASM and see if our conversion will implement it on runtime. That's basically pretty much it. Right.
So just to make sure, so do you have WASM running on Raspberry Pi or not?
Yes, we do. But something also happened. The WASM itself, the WASM runtime itself can run on Raspberry Pi right now, but we haven't successfully run the WASM file yet, because there's like something like well, above all, the WASM itself is you can see the WASM itself as a translator. You can translate everything like C, Python, or C++. First of all, translate to WASM and then go to the device. But it's not kind of universal. We tried two things. First of all, we use a C convert to WASM and trying to run that on WASM runtime. However, this WASM runtime was used for the Rust, and it's failed. When we switch to Rust, it's success. So it's not like pure translate and you can implement in your WASM on any sort of runtime. It's not something not like that. Also, if you use a C and your WASM runtime supports C, but however, your WASM requires for client 8 and you use a client 6 and convert those to .wasm file, your runtime cannot run that. It just can't. Right.
Okay, great. I think let's move on because
all right.
We're short of time. So next one.
Okay. Hi everyone. My name is Chu Yang. My teammate is Yuan Xiang. So we are working on the project of height post estimation using Essence wearables. The goal of this project is to estimate the height post using IMU information collected from the Essence wearables connected with Essence app in an Android phone. And we collect the sample data are the facial recordings and IMU information, and generate ground truth tables from facial recordings. And we also design a CNN and LSTM algorithm for the time series forecasting in height post estimation. And we plan to use estimated height post to create and show emojis for users on an Android device in the end. So we first recorded facial videos and IMU information at the same time and generate ground truth tables using the videos with matured height post estimation algorithm. So for the matured height post estimation algorithm, we found some pre-trained models online, and finally we decided to use the Google Cloud Vision API. And it's a good pre-trained model. And we first chopped the video into frames, almost 3 milliseconds per frame, and use the Google Vision API to detect faces and find the current positions in the frame. And we need to build a CNN and LSTM model for the time series forecasting using the collected IMU information as the training data, and also use the previously generated ground truths as the labels of the training data. And it's basically a regression algorithm with exact position in the pen, tilt, and row these 3 coordinates. And we need to modify the last layer of the neural network and loss functions based on this regression algorithm. And at last, we plan to use Android Studio to develop an Android app and to show the emojis of users just using the IMU information without camera sensors. So here's our data set. The first figure is IMU information consisting of the timestamp, accelerometer, and gyroscope data with the essence variables. And the second figure, yeah, of course, it's me. And it's the example output frame for the face detection in the frame with pan, tilt, and roll coordinates using the Google Vision API. And the third picture is facial recordings. The data on it are timestamp, pan, tilt, and roll data coordinates. And combining the first and the third data set, we have our input data with IMU information and facial recordings. So let's take an overview of our CNN and STM model. So our input data coming from the essence variables processed by the 4 convolutional neural networks to extract features. And next, the 2 LSTM dense layers perform a nonlinear transformation. And the final dense layer with the rectifier linear unit as the activation function outcome with linear dense output layer. So currently, we collected our sample data, facial recordings, and IMU information as training data, and generated ground truth tables as a label of training data. And we are still training our CNN and STM model for the time series forecasting. So next, we are gonna after successfully building the model, we are gonna optimize this model and improve its accuracy. And in the end, we need to develop the app, load the model, and create emojis with estimated these 3 coordinates to realize the implementation. I think that's it.
So just to make sure, so you are looking at the orientation only in the horizontal plane, right? Or is it like all sort of?
All sort of.
All.
Yes.
Okay. And Swapnil, what about in your project? It's only lateral, right?
No, same.
Same thing. Okay. So it would be good to compare the results, right?
Okay.
Yeah. I have a question. So are you like fusing the camera data and the essence data?
No, camera is just for ground truth, right?
Yes, camera just for ground truth.
So your input is like what essence?
Input is the accelerometer and gyroscope data
from the essence.
Yes.
Okay. And how are you planning to like account for the variable something rate without extracting the features? Because the data from the essence is not something that is variable.
Do you have like the label for each and every point of your data?
Yes. So basically, we for example, we record a video first, and we chop the videos into frames every 30 milliseconds, and using the Google API to find the 3 coordinates for in each frame to detect the faces, and like I said, record the facial videos and IMU information at the same time. So we will find the overlapped timestamps, yeah, and combine the IMU information and the frames.
At each point, you know even in the basically you know the entire time series for each frame.
Yes. Yeah. For each 30 milliseconds, yeah, by the OpenCV libraries.
Okay. So our thing is.
Yeah.
Okay. Any other question? Okay. Last but not the least.
Thank you.
Thanks.
Hello everyone, my name is Yifan and my partner is Zeyuan Wan Li. Our project is named IBID, which stands for Interaction Between Intelligence Devices. But here we focus on intelligent cars. So the motivation. Our project comes from a simple question. What if all vehicles on the road are run by computers somehow in the future? So currently we are witnessing a very great improvement on autopilot algorithm, which gives user abilities to do not control their vehicles but run by computers. But autopilot cars are not that much today, but it could be increased in the future. What if somehow all the vehicles on the road are run by computers, and how they communicate with each other to improve the traffic, for example? That's the point that we want to contribute. So the project goal, we want to build an algorithm for autopilot vehicles, which can provide a reliable communication protocol between two or more vehicles. And the deliverable part here, which is what we want to show at the end of this quarter, is instead of adding onboard sensors, we want to make the following cars to be somehow blinded, but still autopilotable based on the information shared from the leading car. Technical approach. For the hardware part, we use Arduino Uno for the following cars as a computational module. And for the leading cars, we use Raspberry Pi 3B Plus, which gives us more computational abilities to handle more complex tasks. There are ultrasonic sensor and IR detectors installed on the leading cars. For both leading and following cars, we use L298N motor drive control to control the running of its motor. And for the Arduino Uno, since it does not come with Bluetooth and Wi-Fi in functions on the board, we use two chips to add these features. We also have 3 Bluetooth pins for indoor positioning, which I will talk a little more about it later. And last but not least, EchoDot. That is the next step. We want to enable the voice controlling of our vehicles. As to the software, all the cars interact with each other through Bluetooth channels. And the indoor positioning was based on RSSI, which stands for Received Signal Strength Indicator. We control Raspberry Pi through Wi-Fi channel, which is by logging to the command line through SSH. And we are going to build the voice control based on Alexa services. Current status. First, we have realized the interaction between two cars. Now we have leading cars equipped with multiple sensors, while the following car have no sensor but just the Arduino Uno computational board. And the leading cars will transmit the detected environment information to the following car as some kind of a guide. And the leading car will also send the speed information to the leading cars to maintain the same speed between the leading cars and the following cars. The leading cars can control the following cars by sending commanded signals via Bluetooth channel, which can be stopped, run, pause, speed up, and slow down. Secondly, the indoor positioning via RSSI. We have put 3 Bluetooth beacons at the 3 corners of the room we used to test our car. We scan the RSS value and doing data filtering to find out the signal from 3 beacons instead of other Bluetooth devices. We calculate the distance between cars and all 3 Bluetooth beacons. And based on that information, we can represent the relative current coordinates of our vehicles in this room based on the relative coordinates of that 3 Bluetooth beacons. Thirdly, the remote control. Since we using the command line now to control our Raspberry Pi car, which is a leading car, we want it to be not limited by our local network. So we added NAT to expose the local IP of Raspberry Pi car so that we can remotely control our Raspberry leading car from, say, like a different network environment. But next steps. So we are going to add voice control, which is based on Alexa's. What we want to realize is that we can not only control the leading car, but also the following car through voice. For example, we want to see like car 2, please stop at the place you are currently now, and like car 3, please go ahead and keep following the leading cars. Also, we want to expand it what we have realized on the 2 cars systems to be on the more cars. And we want to build an interaction system and implement a group control of at least 4 cars at the end of this quarter. Yeah, and that is. Any questions?
So, just to understand, you're assuming that the cars, you know the positions of all the cars.
Yeah.
So,
I mean, for the leading car.
okay, so what does following car know? I'm kind of confused. So you have this whole localization system that you have created.
Yeah, but that's
that is
for
only giving the leading car, right?
Yeah, that's giving the leading
So
car.
how does the and you also said that the following car does not have any sensors, right?
Any sensor for now.
So what makes it not collide with the leading car?
Pardon me?
Like, if the following car doesn't know anything, then how does it? How do you prevent it from colliding into the leading car?
Oh yeah, that's what we use. That's the function of the sensor on the leading car. So we have sensor not only facing towards the front to avoid barriers, but also get the location of the following cars. That's how we make the following car to be somehow blended, but still autopilotable. Yeah.
Okay. Others, any questions? Great. Thanks.
Thank you.
Okay, we are done. Just in time. So the final exam slot, we'll run it the same way, except that since it's a 3-hour slot, so I think you'll have like 9 or 10 minutes for the presentation, but similarly structured. And I still don't know what the room assignment is, but if it is one of the rooms which is next to other final exams taking place, then I'll find kind of some seminar room for it. But I think it's December 9th, Monday, 6:30 to 9:30 p.m. I think that's the exam slot. So just keep that in mind, but similar in style. We'll kind of run it the same way. And for your report and all, you will have until the Friday of that week. So you can still take time. So whatever you have at the time of the exam slot, just present it. Okay, great. So see you guys on Wednesday. Any questions, by the way, before we? Yeah. So see you on Wednesday. I know Wednesday evening is before Thanksgiving is not exactly the best of the time, but I'll record the lecture. So yeah, those of you who have families to go to, go ahead.